The first thing we're going to do on this worksheet is draw the orbital diagrams, which are also referred to as box diagrams, for beryllium and boron. Beryllium and boron are both really small elements. One has 4 electrons, the other has 5, so these are going to be pretty straightforward. So right here, I think I'm going to draw the beryllium orbital diagram, and then I'm going to draw the boron diagram over here, and I want to start with the 1s orbital, and after that is the 2s orbital, and then I'm also going to draw in the 2p orbitals. I'm not sure exactly how many orbitals we will need, but this is definitely going to be enough. So boron, because I have that one handy, that's got 5 electrons in it, so let's fill those 5 electrons in. There's 1, 2, 3, 4, 5, and beryllium has 4 electrons, so we'll draw those in 1, 2, 3, 4. So for the beryllium, we didn't need these 2p orbitals, but it's fine to leave them there empty. On the diagrams, we're going to identify the first electron to be removed from beryllium and boron. So when electrons are removed from an atom, they are removed in the reverse order that they are added. So it's like the last electron that gets added is the first electron to get removed. The last electron that we added to beryllium was this guy right here. I'm just going to draw it pink. And then for the boron, this is the last electron to get added, which means both of these pink electrons, these are the ones that will be the first electron to be removed. So when the electrons are being removed from beryllium or boron, it tells us that the first electron to be removed from boron, this guy right here, is actually a lot easier to remove this electron than it is to remove the first electron from beryllium, and we're supposed to come up with an explanation about why. So what we want to do is think about what the electron configuration looks like right now, and then sort of visualize what it's going to look like when we remove that first electron, so we can kind of imagine that situation. Right now, for beryllium, when that electron is there, all of the electrons are in pairs, in sets of 2, and also all of the orbitals are completely full. And that's a really good situation for any atom to be in. When we pull that electron out, which way do I gotta go? When we pull it out, we now have an orbital, the 2s orbital, that is incomplete. It's not full, and that's not as stable. The atom is not as happy when one of its electrons has been removed. For boron, this electron right here is the one that will be removed. When we look at boron right now, we have a full orbital, and then a partially filled set of orbitals. When we remove that electron, look what we have. When we remove that electron, we have 2 perfectly filled and very complete and happy orbitals, and nothing partially filled. So when that 5th electron is in place, there's that partially filled 2p level, and when we remove it, everything is just perfect and complete. So our explanation here is that the beryllium has all of its orbitals full. All of them are totally full. And this sort of situation, anytime we have this situation where all the orbitals are full, this makes it harder, in terms of energy, harder to remove an electron. Everybody's got a partner, and when you pull one of those electrons away, it disrupts that beautiful symmetry. Similar thing we're going to look at next for nitrogen and oxygen. So let's move over on the periodic table. We'll find nitrogen and oxygen. One has 7 electrons and the other has 8. So we're going to draw those energy diagrams. Nitrogen will be on the left. We need a 1s, a 2s, and 2p. Nitrogen has 7 electrons, so there's 1, 2, 3, 4, 5, 6, 7. Remember the rule that when we're filling up orbitals that have the same energy, so when we're filling up the 2p orbitals, they all have the same energy, they're all at the same spot on the diagram, we put 1 electron into each orbital before we put 2 electrons into any orbital. So everybody gets 1 before any gets 2. This is going to be for oxygen, which has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And again, we're going to highlight the first electron to be removed. The last electron that I drew for each one of these is the first electron to be removed. So that's now in pink. And we want to imagine a situation here. Why is it easier to remove the first electron from oxygen and harder to remove the first electron from nitrogen? We'll do the same type of analysis. So for nitrogen, right now, when we were looking at beryllium and boron, we were really focusing on the orbitals being completely intact and completely full. That's not the case with nitrogen. Nitrogen has these 2 orbitals that are completely intact, but the 2p orbital, every one of the orbitals is half full. Every one has 1 electron. And when we pull 1 electron away, this is what it looks like. So this is the kind of the difference that we're looking at for nitrogen. With oxygen, again, we have totally full, and then the 2 p's altogether not totally full. So we're looking at this, and when we pull that 1 electron away from the oxygen atom, this is what we end up with. So we can kind of imagine the differences here. Now, keeping in mind that Mother Nature loves symmetry and loves everything to be balanced and perfect. So when we look at the oxygen, specifically what we're looking at right now, when that electron is there, that pink electron is there, we've got, two electrons in one of the orbitals and then 1 in the other 2. When we get rid of that pink electron, all of the 2p orbitals look exactly the same. Like there's that great symmetry. For the nitrogen, when that pink electron is present, all of the 2p orbitals look the same. When we pull it out, we lose that symmetry. So it's a different situation than with beryllium and boron, but it's the same overall concept. When we pull the electron away from the nitrogen atom, we're taking away its symmetry. When we pull the electron away from the oxygen atom, we're giving it symmetry. We're creating some symmetry. So we're going to say, like the way that you would find this worded in a textbook is that nitrogen has all of its orbitals either completely full, that's going to be the 1s and the 2s orbitals, or half full, exactly half full, and that's the 2p orbital. It is exactly half full. And this situation is harder, this sort of configuration is harder to remove electrons. It's a lot easier to remove electrons when your orbitals are not all completely full or completely half full. Now explain how these answers are consistent with what we've learned about the electron configuration and Hund's rule, saying that, again, that we like to completely fill all the orbitals before we move on to a higher energy level, because that is a great stable configuration for our atoms. And also we like to see that we half fill orbitals that are like, let's say 2p's or 3p's or 3d's, half fill all of the orbitals before, let me add 2p, 3p, etc. Half fill all of them before completely filling any of them. Again, trying to maintain that symmetry and the balance among the different orbitals.